Allora, buongiorno a tutti. Inizieremo tra poco questa lezione importante e facciamo una verifica di audio e video. Se mi potete scrivere sulla chat un momento per verificare e poi naturalmente accetto domande su quanto abbiamo visto la volta scorsa e comunque rivedremo alcune cose attraverso un'esercitazione. Audio is good. Okay. Sorry, I have to switch to English. Forgot once more, once again. So let me pull up the So if you have questions about what we saw last time, please go ahead on the chat. So, okay, it's time to start, and what we will do today is to go through quickly about what we saw yesterday about the coherent demodulator, I would say also decoder, and then show you how this demodulator works by simulating it on a Matlab code. The Matlab code is available on my website. The code that is on the website is slightly more complex than the one that I will show today. The one that I will show today is exactly what is contained in the slides. Okay, so you can feel free to play with it. And the fundamental way of working of the coherent demodulator is to essentially take the scalar product of a transmitted waveform corrupted by noise with a waveform that is generated on ground. These waveforms are generated in a computer, so we work with digital samples. We saw a particular modulation, which let me pick up the pen. This modulation is called binary phase shift keying, and by convention we say that we transmit bit 1 if the modulated phase of the carrier is 0, and bit 0 when the modulation we add a phase equal to pi. So we have a modulated signal cosine omega carrier t plus phi, but phi can be either 0 or pi, and therefore we have these two possibilities. All right. The way in which we decide whether the bit, transmitted bit, was 0 or 1 is to take the scalar product of a deciding waveform d, which for us d of t was cosine omega ct. So we take this scalar product over the bit duration. Remember, t bit is the bit duration, and we decide whether bit 1 or bit 0 is transmitted according to the sign of the outcome. If the sign is positive, if the scalar product is positive, we transmit bit 1. If the scalar product is negative, because we have minus cosine omega ct, therefore we transmit bit 0. We saw that unfortunately the channel is noisy, so there is always noise added to the measured, the recorded voltage, and therefore the scalar product is the sum of a part which comes from the signal and a part coming from the noise. We identified an important quantity which we call the energy per bit, which is nothing but the square of the signal integrated over the bit duration. Okay, integrated over the bit duration. And since the average of the cosine square over a cycle is 1/2, therefore this energy per bit, E bit, contains this factor of 2 and is equal to a square T bit divided by 2. We are assuming, remember, that there are many cycles before we have a bit change, and the bit change is reflected in an angular point in a change of the sign of the cosine of the waveform. So we computed separately the power, the variance of this term, and this term is very easy to compute. So the variance of the noise term Remember that this is a random variable, which has a variance sigma n square, which we computed, and is equal to t bit n0 over 2. Okay, this is the important thing. So the ratio, roughly speaking, the ratio between AS and AN is of the order of energy per bit. So this increases, let us say, is proportional to t bit divided to the square root of t bit, because the variance is proportional to t bit, and the standard deviation, which is the square root of the variance, is proportional to the square root of t bit. So AS divided by AN is proportional to the square root of the bit duration. So if we want to increase the signal contribution to the scalar product over the noise contribution, we have nothing to do than increasing the bit duration. But of course, increasing the bit duration implies a lower bit rate, so a lower ability to transmit large volume of data, because the bit rate, which we can call R or RB, is equal to 1 over t bit. All right, and we will see all in practice. So we did this computation, etc. And we, in the end, computed this ratio, A square over sigma n square, which you can see is proportional to t bit. Therefore, the ratio, the square root of this is proportional to the square root of t bit. And this ratio, this is the important thing, is a function of a quantity EB over N0, or the energy per bit over the noise density in 1 Hz. And remember how we defined N0. N0 appears here when we take the correlation function of the noise, which is a delta function, and N0 is the variance of the noise, can be seen as the variance of the noise, not of the output of the matched filter, of the demodulator, but the variance of the noise. All right, now the next step is to relate this EB over N0 to the carrier power, and we did this pretty simply. This is the equation which relates the carrier power to the signal S. So the carrier power is the energy of the signal divided by the duration of the bit, and therefore is E bit over T bit. And if we want to introduce the quantity N0, we divide this by 1 over, multiply by 1 over N0, okay, and obtain C over N0. Therefore, this is equal to 1 over T bit, E bit, divided by K system noise temperature, okay, because we know that N0 is equal, the variance of the noise is equal to K system noise temperature. All right. So the quantity energy per bit over n0, which is the ratio between the variance of the signal, let us say, over the variance of the noise, determines the amount of errors, the number of errors that we can commit, that the decoder, demodulator can commit. And we saw what is the relation. Bear in mind this curve, okay, the blue curve, which is the one which applies to binary phase shift keying. And we said that in order to have an error between, a bit error rate between 10 to the minus 6 to 10 to the minus 5, we have to maintain an energy per bit roughly in this interval around 10 dB. So this is the ratio, 9 from 9 to 10 point something dB. Okay, and the bit error rate, if we want to be this bit error rate, since the bit error rate here is defined by this quantity, okay, the bit error rate determines the carrier power that we need. So if we want a given EB over N0 such that the bit error rate is between 10 to the minus 6 or 10 to the minus 5, we need a given carrier power. So we need that the carrier over noise power multiplied by t bit must be equal to the value that we have set, okay, 10 dB, let us say. So this determines the carrier power and the bit duration, and we can play on two things, either on C, the carrier power, or the bit duration. If we have a large carrier power C, then we can afford a low t-bit, small t-bit, small bit duration, and therefore a higher data rate. But if the carrier power is low, then we need to increase t-bit in order to maintain a constant value, because remember, EB over N0 determines the amount of errors that we make in a second. So, questions, and now we will move after this this introduction. We will move to the Matlab code, and there are questions. Does TS include also the antenna? Of course. Is the system noise temperature, so all the noise that is that arrives at the digital receiver, because remember what we are doing is digitally sampling voltages across a dipole in the end. So we record the electric fields, but these electric fields are transformed into voltages. And if you have galactic noise which comes into the antenna and reaches the receiver, that noise appears in the stream and therefore contributes to sigma n square. Okay? So it's important, it's everything. Now, let me erase all this, and we will move to the Matlab code. So let me pull up the Matlab windows. Just a little bit, just a moment of patience. Because I have to look at the full screen. Okay. I tested it yesterday. I hope it works. And let me see if it works. Okay. All right, now let me see. I think I have to. This is very strange. Let me see. It should be magnified because otherwise you won't see anything. Just a moment of patience. Let me see if it gets magnified or not. One moment. I need to do something. Yeah. Okay, right. Now I adjusted it yesterday and I hoped it could work. Okay, do you have, can you read the content of the code? Please give me a feedback on the chat. I will wait. Okay, yes, very good. So let us go through what this code does. As I said, it's not exactly the one that you may have downloaded from the website. This code, the one that I will show now, is exactly the implementation of the equations that we just saw. The code on the website uses as a deciding waveform a complex exponential. So it's made up of a sine of cosine omega t and a cosine of omega t. It's more complex, slightly more complex, visually more catchy, and also more precise. It's closer to the actual way of working of modern digital receivers. But I prefer to show you here exactly what we did in the slides in the previous lecture. So let us start from here. You can see the arrow. Follow the arrow. There is no laser pointer here, unfortunately. And I start by constructing a sequence of voltage samples. I work with power of 2, so the number of data, and each data means a sample of the voltage. of the carrier and the modulation and the noise. So I have 32,000 2 to the 15 samples. One could increase it. It's not a problem. You can play with it. So this is the sequence length. I construct here a vector which contains an ID in the sequence for each sample. I've not specified, remember, I've not specified how often these samples are taken. If it's 1 megahertz, the sampling frequency, then is 1 microsecond the sampling frequency, and so on. But it doesn't matter, because we are working with a digital system, and therefore we can go to physical units only afterwards, at our leisure. And in this sequence, I include, for example, 128 symbols or bits. There is a slight difference between symbols and bits, because many symbols can constitute a bit. But for our purposes, 1 bit is equal 1 symbol. Now, what is the duration of the symbol? If I have n data and each symbol lasts 128 samples, the number of the number of bits is equal to n data divided by the number of bits. I impose here a frequency of the carrier. Remember that omega c times bit duration must be much larger than unity. And the digital frequency that I'm imposing is 124, which is, not surprisingly, again, a power of 2. Then this is another important parameter. I impose a noise amplitude. Since I work with dimensionless units, my waveform will be cosine omega ct. So the amplitude is unity. I work with unitary amplitudes. What matters, of course, is the ratio between the amplitude of the signal and the, let us say, amplitude of the noise, or the standard deviation of the noise. And here, for this test, then we will play a bit and we will change things. I have taken a noise which is twice as large in terms of standard deviation as the signal, so is larger than the signal. Okay? And we will play with these parameters. So let us go quickly through the code. I first compute a sequence of bits. And to generate the sequence of bits, there are several ways. Here I generate, I use this function that Matlab provides. The function rand generates a random number with distribution, uniform distribution in the interval 0, 1. Okay? So a random number uniformly distributed between 0 and 1. Since I want to negative and positive identify the bits according to a different criterion with respect to 0, I subtract to the output of the function rand So this is a sequence of, in our case, 128, and a symbol is equal to 128, see? So this is the sequence of bits. I construct a sequence of 128 bits by taking the output of this function rand. Remember that this is a vector of dimension 1, so the number of columns is 1, the number of rows is the number of bits, and I subtract 0.5. If 0.5 is bit sequence minus 0.5 is larger than 0, I have bit 0. Otherwise, I have bit 1. So it's a way to procure a random sequence of zeros and ones. There are here other methods using the function polyval that you may take a look at. It's another way, but in this case, I have a fixed sequence of zeros and one. Okay, here I have a random sequence of zeros and ones. So every time I run the code, I have a different sequence. Then I need to apply a phase shift, and I have to define the phase shift that I apply. So this module here applies the phase shift. The function fix provides the nearest integer to j1. So I take for all the data sequence, I take this number, which is jj1, which is the index in the sequence divided by the bit duration. And therefore, I want to apply, the goal of this loop is to apply the same phase shift to all the bits in t-bit, in a duration t-bit. Okay? So all the samples corresponding to 1 bit have the same phase shift. And let us move on. This is a figure, we will see the figure. This is the sequence of bits. Then I generate the noise, and you see I use the function rand n stands for normal. This is a function which generates a sequence of n data randomly distributed with unit variance. If I multiply this random number with unit variance by the noise amplitude, I obtain a sequence noise 1 here, which has a variance equal to, in this case, 2, equal to noise amplitude. Okay, so I start from this, I generate the vector of the carrier, all the samples, so this is cosine 2 pi f0 divided by n data, because everything is normalized to, I'm dealing with a digital system, so t is the index, t is the index of the sample, and you see I have to divide by t by n data in order to obtain the carrier. And we will see what is the shape of the carrier. You can go through this equation by yourself. It's not complicated. Now I compute the energy per bit, which is the way in which I compute the energy per bit, I take the carrier, the vector of the carrier, multiply by its transpose, therefore I take the scalar product of the carrier, which is the sum of the squares of the samples, and divide it by the number of symbols. This is the energy per bit. I have to divide by the number of symbols because, of course, I've done it on the whole sequence and not on the single bit. So I have to reduce by this amount. Then I compute the n0, the quantity n0, and I do essentially the same thing. So I take the noise sequence scalar product with itself. The scalar product, remember, this is noise times noise transpose. This symbol prime means transpose. And this is the scalar product of these two vectors. If I want n0, the variance of the noise, I have to divide by the number of data and data. And I can compute here the fundamental quantity, which is EB over n0. Okay? EB over n0 is equal to energy per bit divided by n0. Okay, let us move on in the structure of the code. Now I have to apply the modulation, the phase modulation. And the phase modulation is done very simply. A modulator is nothing but a multiplier. So we have an incoming signal which is modulated, and modulation means multiplying. So I multiply the carrier by the modulation, and the modulation is cosine of pi multiplied by the phase that I've decided above. If this phi underscore m is equal to 0, then cosine is equal to 1, and I have bit 0. If phi of m is equal to 1, then cosine of pi is minus 1, and I have minus the value of the carrier. So this corresponds to applying a modulation of an advance in phase equal to pi. Then I construct a sequence S, which is the sum of the modulated sequence plus the noise that I built. And I plot, this is a plot that we will see, etc., etc. I do also an FFT of the resulting signal, a fast Fourier transform, and we will plot the outcome of the fast Fourier transform. We will see it here. And then this is the demodulation phase, the demodulation stage. So I have to multiply this sequence made up by carrier plus noise, modulated carrier, I should say, plus noise, and multiply bit per bit, take the scalar product, with the deciding waveform, so over the bit duration. And you can see the outcome here. So I put in this buffer all the samples corresponding to 1 bit, and I cycle over the number of bits. So this vector buff contains one data corresponding to 1 bit. And then I have nothing to do that than to multiply the bit samples here, take the scalar product with the deciding waveform, and the deciding waveform is this one, is cosine 2 pi f0 tt over n data, so is cosine omega c t in our equations, and look at the scalar product. If the scalar product is, I have to normalize it by the number of symbols, by the way. The dot product that I obtain from this stage, remember I have to divide by t symbol, so the symbol duration. This comes again from the equations that we have seen. And if the scalar product is smaller than 0, then this means that the waveform contained bit 1. If is larger than 0, the waveform contained bit 0. Then I do a number of plot. I compute the number of errors. So I compute the original sequence that I know that I generated in the beginning with the outcome of the scalar product, and I see whether they match or not. And in the end, I will write the number of matches and the number of errors. All right? So we are in a situation, remember, let us go to the beginning. We have 128 symbols. And if you divide 2 to the 15 by 128, you will see that there are 256 samples per each bit, because 128 multiplied by 256 is exactly 2 to the 15. And we have a symbol duration which is defined accordingly, and we have a noise amplitude which is twice the signal amplitude. Okay, so we are the carrier is below the noise. Let us say. Let us see what is the outcome. Okay, so I run the code and I see a number of interesting things. First of all, this figure here, figure 1, that I hope you can see, I can also magnify a bit. Okay, contains the bit sequence that has been generated by the random function. So bit 0, we have a number of zeros and a number of ones, and this is the bit sequence. So for example, here you see we have the random number generator has provided a fairly long sequence of zeros. They should be 5 zeros, consecutive zeros, and so on. All right? So this is the bit sequence. I can eliminate it, delete it. This is also something interesting because it gives you an idea of the signal plus the noise. So the red is the carrier, the blue is the carrier plus noise. So the blue samples are the one that will be fed into the scalar product and into the demodulator. Let us magnify here a portion of it. So you can see the modulation. Okay. Let me magnify further this portion here. And you see, you notice immediately one thing that is a consequence of the fact that we have chosen to modulate the carrier in a way that is not the way in which is done in truth. So you see the carrier, the red curve, and here you see a jump in phase. Okay, you have a jump in phase, a discontinuity. This means that the bit, there was a bit transition from 0 to 1, or vice versa. And here we have another one, you see? There are better ways to make things continuous and introduce a discontinuity in the first derivative, which is desirable. But for the goal of this demonstration, this is sufficient. So you know that at least from here to here, from here to here, there is one bit. There may be more than one, actually, because we don't know if there was a bit change in between, we wouldn't see, and the bit, if there wasn't a bit change, but the bit duration is such that you have a bit transition here, you wouldn't see it. You see the bit transition only when the bit changes from 0 to 1 or vice versa. Okay? Or vice versa. So this tells you also what is the effect of the modulation. The effect of the modulation is to induce these transitions every time we have a new bit. So let me close it. And here you see the same thing, the modulated carrier plus noise with all the bits. And again, let us magnify to see whether by eye we can see some bit transitions. Here, for example, there is a number of them. And here we have the bit transitions. But given the fact that you have a noise which is twice the signal, you don't see by eye the bit transition, the fact that you have a bit transition. Do you agree with me? There is no indication, for example, that here there was a bit transition. No evidence. Why? Because we have the signal, the carrier, modulated carrier is buried in noise. So only the demodulator, the scalar product, which in technical terms is called the matched filter, is able to identify the bits. What time is it? It's time to stop, and we will make this stop here, and once in a while we will I will do it on time. So it's noon, it's 1 p.m. and we will reconvene at 1:15. Okay? If you have questions, please go ahead. In the meanwhile, I will magnify this region of the spectrum, which is somewhat interesting. Why it doesn't move? Yes, indeed, it's somewhat interesting. Okay, so I magnified the region of the spectrum near the carrier. The carrier is the red line, and the resulting spectrum, however, shows a bunch of lines nearby. Okay, so we will stop here, and if you have questions on what we saw, please go ahead. This is an important part of the course, and I will therefore this section is the one that at the exam I will deal. At the exam, there will be I will be aided by my collaborators and by Professor Genova. Professor Genova will address the attitude, determination, and control. My collaborators will address Daniele Durante and Paolo Racioppa will address the orbit determination navigation part, and I will address this section, this final section, and all the part concerning reference frequency, reference systems, and time and clocks. Okay, we will restart shortly. I've not seen any question on the chat. Okay, we can restart. So I've not seen any question on the chat, and let us move forward. So what you see on the left panel is the power spectrum, which is obtained from the fast Fourier transform of the time sequence of the total sequence made up by modulated carrier plus noise. So here you see carrier and noise. You may notice that in addition to the line corresponding to the frequency of the carrier, there is a number of lines, and all this can be considered a subcarrier. So the spectrum is spread around the line. If you don't modulate, remember you would see just the red line, but the modulation produces this spreading frequency of the signal, which of course is corrupted also by noise. So this is something important to remark. And the width of these blue lines depends on the modulation frequency. So the shorter the bit duration, and therefore the higher the bit rate, the larger would be this spreading of power. So this is an important aspect, and it's not our task, but in telecommunications, well, the spectrum is well known, and these side carriers are well analyzed and described. On the right, in the plot on the right, so I can close this, in the plot on the right, you see the outcome of the scalar product. And this is important because the outcome of the scalar product tells us, you see, whether we have decoded correctly each bit. Whether we have correctly decoded each bit. And it seems we did a good job because each cross is the output of the scalar product, the output of the decoder. And we have a clear separation of the bits which are 0, scalar product, positive scalar product, if I remember well, and bit equal 1 with a negative scalar product. Okay, so the two streams are well separated and they don't tend to mix. This is a consequence, of course, of the fact that the energy, let us take a look at the energy per bit. And the energy per bit is in a window which is behind this. Let me see if I'm able to pull it out. Where is it? The energy per bit. Okay, it's, let me see where it is. Should have been behind this one. But is not. Let us close all these windows. Okay, here it is. So I keep a little bit of space, I pull it out. So we have 128 matches and no errors. And you can see here in this stream the original bit, modulated bit at the transmitter, the receiver bit at the receiver after the demodulation, and here the value of the scalar product for each bit done 128 times. Here, up here, we have the energy per bit, which according to our digital normalizations, our normalization and the fact that we are using a digital system, so we have not attached physical units to any of these results, so you have to interpret this only in relative terms. The energy per bit is essentially 4. Remember, 4 is twice, is 2 squared. 2 is the amplitude of the noise in terms of variance. If I take the square of that variance, I obtain 4. And the ratio EB over N0 is equal to 32. So no surprise, according to the curves that we have seen, that the energy per bit, with such a large energy per bit, there is no error. We are not committing any error. No surprise. So, since we have a large energy per bit, we can try to increase the number of bits, increase the bit rate. And therefore, instead of transmitting 128 symbols, we can try with 256 and see what happens. Okay, let us run. And again, you see, we have a fairly good separation between the two streams. So now we have transmitted more bits. The bit rate has doubled. And still, we have 256 matches and no error. What is the energy per bit now? The energy per bit is 15. So we are getting a bit closer to the limit. You see, now we have an energy per bit of 64. The noise level stays the same, about 4, and we have, therefore, an energy per bit which is half the previous one, about 16. Let us try reducing the bit rate again. We expect now a bit rate of 8, an energy per bit over n0 of 8, because if we reduce, yes, an energy per bit over n0 stays the same. This quantity is reduced by another factor of 2, so EB over n0 should be around 8. And we have to expect perhaps some errors, but is unlikely, because if you remember well the curves, you have to go close to unity to find a large number of errors. So let us put here 512, okay, and see what happens. Now the situation, you see the two clouds are much more dispersed, and there are some points which are close to 0. And we don't really know whether this is an error or not. All right? Let us see what is the outcome. We have one error, only one. We are running in a dangerous situation, so we have one error over about 500 transmitted bits. And one could see if with the energy per bit, which is equal to 8, this matches more or less the theoretical prediction. Remember, however, that we have a random realization of the bit sequence and a random realization also of the noise sequence. So maybe if we run it again, we find a number of errors which is different. No, we find still one. Let me try another time and see if the number of errors. Now we find 3 errors, because remember, it's a random process. We have a different structure of the noise, different realization of the noise. So no surprise. Okay? And if we want to go even a bit further, which may not be a good idea, but let us say 124, so increase the bit rate even more, well, in that case, I expect a large number of errors. You see, the clouds are much closer to each other, and indeed, the number of errors is 30. The other way, let us return to the original situation when we had 128 symbols, bits. And this time we play not with the bit duration, but with the amplitude of the noise. So the carrier over noise power decreases. And let us see if we have one unity. There shouldn't, no, in this case we are going in the opposite direction. Let us say 4. So 4 square is 16, remember. And therefore the energy per bit. You see that now we are transmitting much fewer bits. 128. We are at the original, our original setup. And we don't make any error. The energy per bit, let us see what is the value of the energy per bit. Maybe I skipped it already. Okay, energy per bit over n0 is equal to 8. So a fairly large fairly large number, but nonetheless, it may have been a pure chance not to have committed a mistake. Let us rerun it again. You see that there are some points close to the threshold, which is 0. So they are prone to be errors, but still we don't find any, but we were really, really close. Let us see if another run with a different realization changes the situation. And now we have, you see, 2 errors, because it's a random phenomenon. Okay, so with amplitude 4, this is the situation. If we go to amplitude 8, for example, so a large noise, we expect a much worse situation. Let us run the code, and now you see we expect a large number of errors. In fact, the errors are 16, and the energy per bit here is only 2. And with this EB over N0, you can go on that curve, and we will do it with an energy per bit over N0 equal to 2, we may expect roughly 10% of errors, 10 to the minus 1. And we will, when we finish with this Matlab code, we will go back and take a look at whether our predictions were correct. And remember, this simulator, as simple as it is, does an excellent job in predicting the bit error rates. So if you have questions or if you want me to try different approaches, that would be, I will be happy to answer. So what is the way, in the presence of a large noise or a large carrier over noise ratio, what is the trick that we may apply? Well, we can decrease the number of symbols, increasing therefore the bit duration, increase t-bit, make the symbol longer. And remember that the signal to noise goes like the square root of the bit duration. So here I write 64, and let us see what happens with 64. I run the code, and now I have fewer bits, but still a clear mixture of the two clouds, the positive and the negative clouds. So I expect a relatively large number of errors still. Not much, only one. Okay? Only one in this case. Let us do another run and see what happens. 2 errors in this case. So 2 errors over 64 bits still is a very large bit error rate. Therefore, if we are limited in carrier power because the spacecraft is too far away, or because the antenna the dish is too small, then we can reduce here further the number of errors, of symbols, the number of bits. Let us transmit fewer bits, decrease the bit rate. And now, again, there is a clearer separation, and I expect fewer errors. In fact, we have 0 errors. But is a chance. We are in a dangerous situation anyway. Let us decrease it further to 16. And what is the bit error rate in this? Sorry, what is the EB over N0? 8. We are at EB over N0, 8, which is already suboptimal because we have to have, we must have at least, let us say, 10 or more in terms of bit error rate. So if I go now with number of symbols, I don't remember how many I used here in terms of number of symbols. If I use 32 already, let us do it 32 and we'll probably find the same things. No, I had to go to 16, you see? See, still there is a good separation, so not many errors. But because the bit error rate, because the EB over N0 is equal to 8. If we want to be sure of committing really very, very few errors, 10 to the minus 6, 10 to the minus 5, we go to 16, and therefore we will get a definite clearer separation between the two clouds. Of course, we are transmitting fewer bits. We have increased the bit duration, and we have, however, paid the reliability of the communication in terms of low bit error rate with a lower bit rate, so lower data volume. Okay? Now there is a question on the chat. Changing N0 changes the spectrum of the signal or only the change in TB? If we change N0, of course, so we change the noise amplitude, also the spectrum changes because the random fluctuations that we see also change. So the spectrum changes for sure. And here is what you get. Let us magnify this region of the spectrum, for example. Okay? You see, now all these lines are quite stronger because we have amplified the noise. And if we go closer here, we will still find the sidebands, but now the sidebands are narrower. The power is spread over a narrower region of the spectrum because we are modulating at a lower rate. We have only 16 bits we have transmitted in the sequence. If we increase, and let us go back and see what happens if with this situation we transmit, for example, 124 bits, which is an extreme with this noise amplitude. So let us see what happens to the power spectrum. So here, of course, the number of errors that we are committing is huge. Out of 124 bits, well, 1/3 of them is in error. You see, the number of matches is 700 and the number of errors is 300. So if we go up and we see EB over N0, for example, EB over N0 will be to go way up because we have many bits this time. Okay. EB over N0 is 0.24, so really a situation that you will never find. But let us look at the power spectrum. I will rerun this again, it's faster. So the power spectrum is here. Let us magnify it. near the carrier, more or less the same size of the window. And now the effect is that you don't even see the sidebands, because the sidebands are buried in noise. So they are here, but they are at the same level of the noise. If you want to see them, you have to reduce the noise, for example, let us say 0.1. Okay, so we make the signal to noise ratio very large in such a way we are able to see the sidebands. And you can see that with this huge signal to noise ratio, the two clouds are very well separated, and therefore no errors is foreseen. And let us look at the power spectrum. Okay, you see how broad now the power spectrum is. Okay, so all this shallow hill, this shallow mountain, let us say, is a hill more than a mountain, is a consequence of the modulation, which extends over a much wider region in frequency. Okay? So with this example, and if there are no questions, I would switch back to the slides. I hope it was instructive. So let me close Matlab if there are no questions. And I return to the slides. Okay. I return to the slides. So we have seen the basic steps that the preliminary steps that go into the link design. And look, let us look, we were in a situation where, for example, EB over N0 was equal to 2. Let me pick up the pen again. So we were here in this region, okay? So what is the error rate? Is slightly below 10%. Is between 1% and 10%. And if you remember, this was exactly what we found, okay, for that EB over N0. And you may verify by yourself whether this curve is correct or not. So the knobs, the possibility that the system designer has in sizing the telecom link, which has important thermal power aspects on board, are enumerated in this 5 or 6 steps that we talked about last time. Remember that the ground infrastructure is fixed, so the mission designer can choose a given station based on availability, based on cost, based on geographical location, etc., but it's fixed. And the system designer, however, has to look mostly at what the onboard telecom system has to provide, has to be designed in order to allow the given data volume, the given data rate, according to the mission requirements. Okay, and it would be interesting, if I have time, I will put also a slide on the sizing of this particular case. Is important for JUICE, for the mission JUICE here. This is an interesting exercise that you can do by yourself. So, last time we went on, we will skip all this part and we will describe again antennas. This is the illuminator, the horn. I will show some more pictures. Transponders. The other crucial onboard element is the transponder. The transponder essentially receives the weak signal coming from the ground antenna, decodes telecommands, encodes the telemetry in the downlink, and provides a radio signal, a carrier in the downlink, which is phase coherent with the uplink. The transponder is also used for ranging signal, so it receives a ranging modulation and retransmits it coherently to ground. And this also generates other radiometric observables useful for the determination of the angular position of the spacecraft. So here is an example of a transponder. I have better examples because this is the first generation of digital transponders. Today we can do much more compact objects. This was a very heavy transponder. The mass was 6 kilograms. Today we can have much more performing units with much less power consumption. And for the ground antennas, we will speak about ground antennas a little bit, how they are made. So for deep space, one uses a large antenna, 35 meters, even 70 meters NASA has. NASA has a network which is made up by 70 and 34 meter antenna. The 26 meter antenna network has been dismissed, and other space agencies have smaller antennas, 10 meters. Finally, I would like to mention also the antennas for Earth telecommunications. They have diameters of the order of 10 meters or so. And the end-user antennas, the so-called VSAT, very small aperture terminal, which this can be, for example, the parabola that I have on the roof of my house to receive satellite signals. Okay? Here you see a picture of the antenna in New Norwich. It's a 35 meter antenna. Beam waveguide, rather compact, and you can see that is a Cassegrain mount. Here you see the subreflector, hyperboloid. You don't see, you barely see the aperture here, the aperture. I will cancel it. So that you can see the hole a little bit better, and we will see why there is such a large hole. Okay, these are NASA antennas. This is a 34-meter beam waveguide, and this is a 70-meter. Let me pick up again the pen. A 70-meter antenna here. 70-meter antenna is impressive, but as you can imagine, it's very difficult to maintain the shape, the parabolic shape. So this antenna is used only for S and X band. So wavelength that are not too short, while the 34-meter antennas, they work at Ka band as well. And you can see the basic difference between these two antennas. They are all Cassegrain, and here you can see the subreflector here. But the receiver in the 70-meter antenna is located in the so-called vertex room, which stays here. And the vertex room moves together with the antenna. So if you have to make maintenance, you have to stow the antenna in this position with the dish vertically pointing upwards. And you are working in a relatively narrow space, 3 meter by 3 meter, with all the receivers contained there. This other antenna, more modern, the DSS-25, which is a 34-meter beam waveguide antenna in Goldstone, California. Also, the other one is in the California desert. And remember that NASA has 3 sites, pretty much like ESA. The sites for deep space telecommunications of NASA, the Deep Space Network, are located in California, Spain, near Madrid, and Western Australia, near New Norwich. And they are located more or less, in Canberra. New Norwich is the ESA antenna. It's in Eastern Australia. Canberra is in Eastern Australia, and it's ESA that has a New Norwich antenna in Western Australia. So they are located more or less at 120 degrees each. This ensures that at least one antenna is in visibility of a deep space probe at every time. And the same does ESA. ESA has a slightly less equispaced network of antennas. Has an antenna in New Norwich, as I said, another one in Madrid, near Madrid, in Cebreros, and the third one is in the southern hemisphere in Argentina, near the Andes. Is called DSA3 Malargue. Okay, so the longitude between the Madrid antenna and the Malargue antenna is not close to 120 degrees. It's about 70 degrees, not optimal. Okay, here is a picture of a photo that we took when we visited the Madrid DSN site a few years ago, and you can see the antenna, a 34-meter antenna. You can see it better here. You can see the subreflector pretty well there, the subreflector shape, and again this big hole that we will explain in a moment. Okay, so let us look at what time is it. We have still 7 minutes. This is the classical mount of an elevation azimuth antenna. So we have the subreflector, the vertex room here with the receiver, the second feed, the Cassegrain focus. This is a Cassegrain mount. We have two axes. This is the azimuth axis, so the antenna can rotate to point the spacecraft around this axis. And this one, which comes out of the plane of the computer, is the elevation axis. So there are servo mechanisms and motors. Motors for the azimuth controls are located here near the wheels. There is a track, on which the wheels which allow rotation about the azimuth axis, and each is controlled by motors, electric motors. And there is a motor for the elevation axis as well, and the antenna therefore can point in every direction. Okay? It's essential that the track is plane, is along the local vertical. At Madrid there was one antenna, due to poor geological studies of the soil, which started tilting a little bit, which made pointing very difficult. So what they decided to do is to dismount the antenna and rebuild it 100 meters away, where the soil was more stable. This is same scheme showing the difference between the prime focus mount and the Cassegrain mount. And finally, the beam waveguide antenna. But before showing this, let me show you this diagram, which is more illustrative. This is a beam waveguide. This is a diagram showing DSS 25, for example, a NASA antenna, where you see we have the subreflector, we have the prime focus here, but what is done is that the beam is carried by means of a series of mirrors. There are 4 mirrors and a fifth one down here. Is carried through a beam waveguide, which is a waveguide of a section of about 1 meter. It's very large. Is carried down by means of these radio frequency mirrors, is carried down in the basement, and through a series of reflection reaches the feed. So the feed de facto is located in the basement of the antenna, in the pedestal, so-called pedestal room. This configuration allows a much easier access to the instrumentation. And if there is maintenance to do, is much easier to do working in the basement than in the vertex room. And here you see a scheme of all the reflections that the signal undergoes in a beam waveguide antenna. And all modern antennas used for deep space telecommunication and space telecommunication in general are beam waveguides. Here again another sketch, and this is the interior. These are pictures of the interior of the pedestal room at DSS 13. So you see here, this is the mouth of the beam waveguide, which comes from the top of the antenna. Okay? So the beam is goes along these arrows, is reflected. You see that here we have another reflection mirror, and finally goes into the horn, into the feed. And by rotating this mirror around this axis, one can access to different feeds. For example, this one or this one is a much simpler, operationally simpler configuration. Okay, the radio frequency structure has to be designed extremely well. And here you see 3 beam waveguide antennas located in Goldston, California. I have some additional images of beam waveguide antennas. The waveguide goes here and goes into the basement. Here you see the aperture. So the signal is reflected into this aperture. There is no feed there. The feed is down here. Okay? The feed is down here. And this is a picture of a 70-meter antenna. And here is a picture that I took inside one of these antennas. Let me see what time is it. It's time to finish. And again, we show how much easier it is to handle a beam waveguide antenna than other antenna. I thought I had other plots, but no, next time we will go through this. Let me finish only by showing you what the typical gains are for typical antennas. This is for a 34-meter antenna, if I remember well. The typical gains, you see a text band. Here we are at 68 dBi and a factor of 10 larger at 32 gigahertz. This is for a 34-meter antenna. And here you see the efficiency. Okay. At Ka band, the efficiency is lower than at text band. No surprise, because it's more difficult to keep the surface on a paraboloidal shape with a wavelength, respect to a wavelength that is only 1 centimeter instead of 3.4 centimeters. So no surprise in this. Okay? And with this, I will stop. And next time we will continue, finish and go into radiometric measurements. There are questions. The reason why they are painted in white is because of decreasing TCs. It's because you don't want to warm them up too much. Because if you paint by a different color, the absorption of radiation is larger, and therefore the temperature of the steel increases. You have larger thermal deformations, and therefore it's more difficult to keep the shape parabolic, because the surface is more deformed. Okay, so this is the reason why it's painted white, because you don't want these antennas to be heated too much. There are cases, I can tell you a sort of a story. this antenna can be pointed to the sun without any problem, directly to the sun. But there was a tester at a radio astronomical antenna called Apex, which had a surface which was quite reflective, also to sunlight, and because it was not corrugated. By mistake, an operator pointed it directly to the sun because it wanted to take a measurement of the radiation from the sun at 300 gigahertz, very high frequency. Well, what happened is that in this case it was if I remember well, it was a prime focus or a Cassegrain mount, not a beam waveguide. But the outcome was that the feed melted. The feed melted, and they destroyed the feed because it increased in temperature so much that it melted. Why doesn't you do a straight waveguide, but you use a shape which a rectangle, a cut rectangle? I'm not really sure I understand your question. So you are asking here, why are we doing all this path and not go straight through here? Well, there is a fundamental reason that if you go straight to the pedestal room, you are able to make observations only along the local vertical. You have to remember that this dish has to move at different elevations. Okay? And how can you have a straight line and go straight to and reach the focus at the basement if the antenna is tilted in azimuth and elevation? This mount ensures you that you can track at every position. For example, this mirror and this mirror, these two mirrors, okay, they rotate rigidly with along the azimuth axis, but they rotate around this axis, so out of the plane of the computer, when you change the elevation. So when there are elevation changes, all these mirrors have to change their angle. And it's impossible to have a straight line. You have to make sure that the optic is such that pretty much in a binocular, the optic is such that the RF signal reaches the feed, whatever the elevation of the azimuth is. Okay, so I hope you understood that with a straight waveguide, you can make observation only in one direction. All right. So if there are no other questions, we will meet again next week. I know that you have the second homework to be delivered by midnight on Sunday. I hope everything is going well, and discard all the drawings, and I stop streaming here. Goodbye to everyone. Goodbye.